Welcome, my name is Jason White, a PhD student with the Optimal Robotics Lab, and today I'll be presenting our formulation of a convex motion planner for single-legged robots that generates behaviors in real time without using predefined contact sequences or mode durations. We begin with an estimated initial trajectory, found by warm starting the following control loop. The contact guards along the plan path are checked to estimate the system mode schedule. We then linearize the plant dynamics using nodes along the trajectory as our operating points. The estimated dynamics are used as equality constraints with an objective function that weighs an average forward velocity, average vertical height, and minimizes actuator acceleration. Since the dynamics are discontinuous, we remove the equality constraint and enforce a new initial condition with a new dynamic set. The plan control inputs are applied to the system and integrated with MATLAB's medium-order differential solver. Finally, the new initial state is then used to find the current mode. The hypothesized controller was first tested using a simple point mass model with no inputs during flight. At the fixed height L max, the dynamics change, allowing the optimizer to utilize the control inputs seen here. We also model an actuated spring mass model. The point mass model also only generates forces during stance, but can actuate the massless leg during flight to control its touchdown angle. When we simulate the controller, the simplest point mass model tracks the average speed and height. The same behavior is apparent with the actuated spring mass model, which tracks the desired states at slow speeds and at higher speeds as seen here. Analysis of the exhibited gait cycles indicates that the key markers, such as gait period, are highly dependent on the dynamics and task, not controller hyperparameters such as the time horizon. We further test the controller's ability to reject large velocity disturbances by applying instant velocity changes, and are even able to modify the objective function to a new height and velocity mid-cycle. Finally, we show that simply modifying the objective function allows the system to easily transition from a cyclical gait to a standstill. Thanks for watching, and I hope you enjoyed my work on convex through contact motion planning for monopods.